In this video, I want to talk about the summing amplifier circuit. So in the previous video, you saw how we can design and analyze an inverting amplifier circuit using op-amps. So here we want to take the previous amplifier design to the next level. So what we have here, we have the op-amp. The non-inverting input is connected to the reference node, so we have the positive, negative VP here. We have the RF again connected from the output to the inverting input. We have positive VCC, negative VCC as we had before. But now what is different here is that instead of only having one input, which was Vs in the previous design, now we have three inputs. So we have Va between this point and the reference node, which is connected to the inverting input of the op-amp by resistor Ra. We have Vb, which is connected by resistor Rb, and we have Vc, which is connected through resistor Rc. But the analysis is the same as before. So what we need to do is we need to write the KCL for this node. And this time I'm going to use the node voltage approach to come up with the equation that shows the relationship between VO and the three inputs that we have, VA, VB, and VC. So let's just write down the KCL for this node. So the voltage here is Vn. So we consider three exiting currents that goes through each one of these. We consider another exiting current that goes through RF, and then another one that basically exits this node and goes through the inverting input of the op-amp. So we have Vn minus Va over Ra plus Vn minus Vb over Rb plus Vn minus Vc over Rc. So these are the three currents that we have here. For the current that leaves this node and enters RF, we have Vn minus Vo over Rf. And finally, we have the In that leaves this node and enters the inverting terminal of the op-amp. So since we don't know its value, we just put it as In equals 0. So now it's the time to use the two constraints again. We have Vp equals Vn, and then we have Ip equals In equals 0. So here we have Ip here. So in this circuit, like before, we have the non-inverting input to be connected to ground or to the reference node. So that makes Vp to be 0. Because of the first constraint, that makes Vn, which is equal to Vp, to be also 0. The second constraint states that Ip equals In equals 0. And that is because the internal resistance of the op-amp is very large. So now that we have this, let's just rewrite this by now considering the two constraints. So we have constraint 1, constraint 2. I want to rewrite this using the constraint. So we have negative Va over Ra plus negative Vb over Rb plus negative Vc over Rc plus negative Vo over Rf equals 0. So now if I rearrange this, to basically have VO on the left side and the rest on the right hand side of the equation, we end up with this equation: VO equals negative RF over RA multiplied by VA, negative RF over RB multiplied by VB, and then negative RF over RC multiplied by VC. Or since we said that this is the summing amplifier, I can write it like this. Put the negative sign outside. We have now RF over RA VA plus RF over RB VB plus RF over RC VC. So that shows the relationship between VO and the three input voltages that we have here. So depending on the values for RF and RA, RB and RC, these weights can be different. So for example, if all of them are the same, RF equals RA equals RB equals RC, what we have for VO is to be negative VA plus VB plus VC. So that's only one example. So as I said, we start from the KCL on the inverting port or terminal of the op-amp, and we write down the equations for the currents that are leaving this node. We have this current, this one, this one, this one, and then this one. This is Vn minus Va over Ra. This is Vn minus Vb over Rb. This is Vn minus Vc over Rc. For the current that leaves this node and goes to the RF, we have Vn minus Vo over Rf. And for the current that leaves this node and goes through the inverting terminal, I simply just write it as In. And now it's the time to use the constraint. We have IP equals In equals 0, and then we have Vn equals Vp. So since Vp is 0, because the non-inverting input is connected to the ground or the reference node, that makes Vn to be 0 as well. So given these equations, the above equation is basically reduced to the below equation, which says VO equals negative RF over RA multiplied by VA plus RF over RB multiplied by VB plus RF over RC multiplied by VC. So as I said before, you have a weighted summation of all the inputs, of course with the negative sign as the output. So one example was to have RF, RA, RB and RC the exact same value. But a very useful example of applying this circuit is for digital to analog converters. So for digital values, let's just say you have a 3-digit number. So you have 0, 1, 0. So you know that for binary numbers, this one has a weight of 2 to the 0, this one has a weight of 2 to the 1, this one has a weight of 2 to the 2. Similar to when you have, let's say, working with 895, you know that this one has a weight of 10 to the 0 or 1. This one has a weight of 10 to the 1 or 10, and this one has a weight of 10 to the 2 or 100, right? So this is a base 10 number, this is a base 2 number. So now let's say you want to convert this binary number into an analog signal. What you need to do is basically to create these weights. So if I say VA is here, VB is the second one, and VC is the third one, right? You can choose the values for RA, RB, and RC to create these weights. So if RF over RA equals 4, RF over RB equals 2, and RF over RC equals 1, that is basically helping us to convert this binary number or digital number into an analog signal. So that is one of the applications of the summing amplifier circuit. So in this video, we went over the summing amplifier circuit and we analyzed how we can come up with the equation that shows the relationship between the output and the inputs of the circuit.